Okay, so I want to look at our next topic, volume by cross sections. And it's an application of the integral. And it's actually pretty cool because you can start using this to not only just accumulate area, but we're going to start to accumulate volume. And so I have a couple of screenshots here where we're constructing these three-dimensional figures based on one uniform shape. And so for this first example, I see it like, over here, I'm starting to construct this three-dimensional shape where every cross section, every little like slice, if you will, is an equilateral triangle. And over here, it's complete. And then, it could be a different shape, like this one, a different region, but I'm picking squares. And if I can add up all the areas of these squares and sort of like stack them up, honestly, it's kind of cool. You get this volume of this three-dimensional shape. My cross sections, could be a semicircle, and you start like slicing these up and adding these up. It reminds me a lot of looking at a ream of paper. And if you think about a ream of paper, each piece of paper is just a sheet thin. But if you stack all of those thin sheets up, you get this rectangular prism, or this ream of paper. Now, it's a lot more impressive too when you can watch it and see it actually in animation. So before we even take notes, I think it's pretty cool just to kind of look here, and maybe we can even watch one of these. Maybe watch this one. It's pretty cool. And again, you're starting with some shape, and they're going to tell you. So this case was the base of a circle, and then you're just going to start constructing a particular shape. And they will always tell you what shape to construct. So in this case, the cross section is a square. And I also want to notice that these squares are perpendicular to the x-axis. Most of them will be perpendicular to the x-axis, but they could also be perpendicular to the y. And so as we start going through some of these examples, this idea of generating this three-dimensional, object that sort of appears off of the page is something that is kind of like our goal in creating that. Is going to be one of the most challenging things, because we're trying to represent a three-dimensional shape on paper, which is only two-dimensional. So definitely play these videos, look at the examples, go back and keep trying to work through some of these problems, and we'll do the best we can. Now, you don't have to be an artist to solve these, but you just have to have at least an idea of what the base shape is and sort of what is your generating function, generating shape. So what I want to do now is maybe start looking at a couple of examples. So now this is in our packet, so we can kind of follow along. Okay, so they're going to give you a region. So they call this region S, and it's going to give you some boundaries. So it tells you what the curve is. Y equals the square root of, x minus 2. And it tells you that I want to be bounded. Okay, so there's y equals square root of x minus 2. Y equals 0, so that's our x-axis here. And x equals 6, which is our rightmost boundary there. So that's going to be the base. So if I think about the, if I think about the animation that was over here, that's like that starting, right? That's that starting graph that's flat that we're going to begin to make these three-dimensional shapes rise above. So we'll go back to here. Now, like I said, you don't have to be an artist. I do, though, like to draw these a little bit with a perspective drawing. So I'm going to take that XY plane, and I'm going to sort of pretend that it's like laying flat on the ground. And you'll see what I mean here in just a second. So I'm going to call this my y-axis. Call this my x-axis, just so I can have a little bit of perspective here. And then, so my actual curve, thinking about like there's 1, there's 2, 3, 4, 5, 6, and then I think it goes up to 2, right? Okay, so 1, 2. So I know that the curve ends here, starts here. And again, I'm just going to draw it kind of as a perspective drawing, and it obviously takes some time and practice, and I have no idea how this is going to turn out because I'm on a tablet, so I've never done this before. So I have that region there. what I'm going to do is start creating squares that are perpendicular to the x-axis. So I'm going to construct a square that if I go from top to bottom, measure from here to here, whatever that distance is, I'm going to create a square that comes off the page. Right? Comes off the page. And then, like there, obviously there's another square, like right here, from whatever that distance is. And whatever that distance is going to come off the page. And whatever this distance is, it's going to come off the page. So it gradually tapers off towards the end. And you don't have to draw a ton of squares to represent this, but I just want to illustrate that we're creating this 3D shape that as the squares, like as you start measuring this distance and this distance and this distance, as these distances get larger, it just means you come higher and higher off the page. Okay. Now, you don't necessarily have to create such an in-depth or detailed image here. What you really need is just to focus on one particular square, one particular slice, like maybe this one right here. Okay, and so if I focus just on that one slice, it's just a general square, and I'm going to like accumulate the area of that square as I start measuring it from 2, oops, pick a different color so I can see it, sorry, from 2 all the way to 6. So I'm going to start accumulating, remember integrals and our accumulation function, starting at 2 to 6, a whole bunch of squares. And the area of a square is just side squared. So I'm going to try to find the area of this square. Now, it's just an arbitrary square. It's just a particular square whose distance is determined really by the function root x minus 2 that's in the plane. So, and again, like I have this kind of like this plane here, like that's my desk, and this thing is just sort of like rising up off that desk. So this distance here is the top function, which is root x minus 2, minus the bottom function, which is 0. So every side length is determined by that particular measurement. And again, I'll just highlight that, like maybe this green here. This measurement right here, the top minus the bottom, or if you look at your figure face on, it's the top minus the bottom. I'm really just measuring that distance. But remember, that's just laying flat, right? This is laying flat right here in the plane. So that becomes my distance, and then whatever that distance is how much I rise up, and area of a square is side squared. So I'm going to take that, oops, I got the thickness, I'll go back here. So I'm going to take that, and I'm going to accumulate from 2 to 6, the top function, which is root x minus 2, minus the bottom function, 0, and each of those becomes the length of my side that I'm squaring. Again, that's this distance right here. It actually becomes a nice function, right? I'm integrating between 2 and 6 of the square root of x minus 2 squared dx. Now, let me just pause for a moment here and just kind of clarify a few things. First, you might be wondering, well, where did that square come from? Where did this exponent of 2 come from? You have to remember or go back to the start of the problem. They're going to give you a shape. They're going to tell you the cross sections are squares. So they expect that you know how to find the area of that shape. So area of a square. What's the formula for area of a square? Oh, side squared. So the structure of that is that square comes from the fact that I'm actually accumulating squares. Now, another thing to think about is that area of a square, area of the square right here is two-dimensional, side squared. And if I think about just like the function of an integral, the function of an integral, basically you raise it up a power. So if I think about, if I have a two-dimensional thing, a square, and I raise it up a power, it should be representing a three-dimensional thing, which is volume. And that volume is going to be created starting at a square of 2 all the way through a square of 6. So again, those squares are accumulating. Again, think about the animation, right? Think about these particular squares are accumulating, hopefully. So, oh, there it goes. Yep. So we're building a square and a square and a square and a square, and we're just accumulating them over an interval. And that if we could add all that up would give us the volume of that shape that is formed. So that's kind of like the background and setup. And I'm spending a lot of time talking about this just because I want to make sure that that part makes sense. Now, from an algebra point of view, squaring a square root makes it a really nice problem from 2 to 6 of just x minus 2 dx. Out of context, this integral right here is one of the, that's one of our easier integrals to evaluate. But getting to this point, the concept and conceptual understanding behind that, that's tough. And so that's where you might want to reset and redo this video and keep looking through all the examples. Because at this point now, you should know how to do this, right? There's nothing new from this point on. Integral, so it's x squared over 2 minus 2x when evaluated from 2 to 6. So we put under 6 squared is 36 over 2 minus 2 times 6 minus, and put 2 squared, so 4 over 2 minus 2 times 2, which is 4. So half of 36 is 18. 18 minus 12 is 6. Minus 2 minus 4 is negative 2. So it looks like we're getting an answer of 8. And remember, what does this 8 represent? Well, the 8 represents the amount of volume. I know my smartboard's got a little crazy here. 8 represents the amount of volume if this three-dimensional shape were filled in. Like if I could fill all that in and it was a solid, it would have a volume of 8 units cubed, whatever that particular value is. And again, just kind of emphasizing the power of the integral. The power of the integral allows you to accumulate something over time, an infinite amount of them for that matter, but it also takes a two-dimensional thing, and because we're integrating it, the power rule says it's going to become a three-dimensional thing. So the next step from area jumps up to volume. Okay, so hopefully that piece makes sense. And a lot of the hardest things about this particular lesson will just be that setup. Okay, so let's maybe do one more in this particular video, and then I might switch gears to another video. I'm going to keep that same region, and this time, though, I'm going to make the regions semicircles that create this volume. So again, I might want to reconstruct the image here. Like I like to draw that perspective. It just helps me, see this and try to create some sort of representation. And so if I think about 1, 2, 3, 4, 5, 6, and then like 1, 2. So the graph starts at 2, 0, and it goes over to 6, 2. Again, I'm just just redrawing the base here. Maybe go with this nice red, kind of arcs up, and it goes down. And so that's the region of the base. But now this time, as I start to construct, my I guess I'll go with this color here. As I start to construct my shapes, when I go from here to here, when I measure that distance, instead of going straight up, that's going to be the diameter of a semicircle. And if I measure this to this, it goes straight up. It's a little bit bigger semicircle. And this to this, measure goes straight up. It's a bigger semicircle. And so I'm continuing to get these semicircles whose diameter is this distance across. Okay, and then here's another, like a little smaller one, again kind of tapers off. And then this one here. Now I'm starting to see some images of like playing croquet. If you ever played that, you get those the little hoops that the ball goes through or whatever they're called. And then a smaller one there, and it sort of again kind of flares out. So we have this three-dimensional, kind of almost like a band shell, if you will, or maybe like it's a Thanksgiving ham or turkey or something. I don't know. And what I want to do is think about, well, what is the general shape of one? What the general shape of one of them is just a semicircle. And so that semicircle right there is what I want to start accumulating area of. And so I need to think about, well, area of a circle I know is pi r squared. A semicircle is just half of that. So half of the area would be 1/2 pi r squared. So that's what I need to accumulate, 1/2 pi r squared. So I'm going to come down here, and I guess I didn't really give myself that much space. So let me just lasso this here for a second. Oops, not you. Bring you over there. Okay. So I'm going to go ahead then and accumulate all of these semicircles. So still starting at 2 and going to 6. There we go. So integral from 2 to 6 of these semicircles. So like 1/2 pi, so it could be like pi over 2, and it'd be radius squared. And then these are in terms of x, because I'm perpendicular to the x-axis. And so then the question is, how do I get this radius? Well, if you notice, like the last one, I'm still going the top to the bottom, right? I'm still doing that distance. But I've got to realize that this top to bottom, that represents not the radius of this circle, but the diameter. So whatever that distance is, I'm going to have to take that diameter and then divide it by 2 to get the radius. So when I'm coming back here to fill out this integral, from 2 to 6 of pi over 2. To get my radius, I'm doing the top function, which was root x minus 2 minus 0, all divided by 2, and that's what I'm squaring. And again, take a minute and make sure this makes sense. There are 2 divided by 2s, and I don't want you to think like, what, like get confused, like where did they come from? This particular 2 is from our formula, right? It's a semicircle, 1/2 pi r squared. This particular 2, this particular 2 right there comes from the fact that my given measurement is a diameter. So this right here is the diameter. I have to divide by 2 to obtain the radius. So I just want to make sure that that part's clear. And then I could say, okay, well, now I'm still going from 2 to 6, pi over 2. And then much like the last one, x minus 2 as a quantity squared becomes just x minus 2. And 2 squared down here becomes a 4. And so this will now be the integral that I'm going to evaluate. And if you think about like what's happening here, it's just like in my classroom that gets close to the edge on the smartboard, it gets a little crazy. This 4 and 2 can multiply to 8. So now I have the integral from 2 to 6 of pi over 8 times x minus 2 dx. And this pi over 8 can actually be factored out in front. It doesn't really matter where you put it. And what I'm going to say, or the reason I'm going to do this, is because some textbooks even just say, if you are going to do something by semicircles, you should always realize that you're going to have this constant factor of pi over 8. And so, some like handbooks or like those, 5 steps to get a 5 in the AP exam, just say, oh, just memorize this. Go ahead and put pi over 8 there. But I want you to show and see where it comes from. But once you realize that, like, that should be a good indication or a good reminder as you start solving these, that you're always going to have this pi over 8 as a factor when you're doing semicircles. Then the rest of the integral, actually, we've already done. Like, we just evaluated this in the previous one. We knew that that value up here was equal to, I think, didn't we say it was 8? Can't remember, wherever that example went. Back here. So we got a value of 8. So now on this example, if that's the case, and we know that the semicircle is pi over 8, we would get an answer that's equal to this 8 times pi over 8, which nicely turns out to okay. And again, that's the volume. That's how much space, how much, right? Space is within this 3-dimensional shape. Okay, so I know I talked a lot, long video. We're going to go through all the other examples, but let me go ahead and pause this and go back to the home screen, and then we will continue to work through these examples.